The last video focused on one-step syntheses that involved either substitutions or eliminations. This video focuses on addition reactions, specifically to alkenes. Alkenes are functional groups in which there is a carbon-carbon double bond. Addition reactions occur when that pi bond is lost and two new sigma bonds form. We saw a number of examples of these sorts of addition reactions, and we observed regiochemical implications to these reactions as well as stereochemical implications. For example, addition of HX, either chlorine, bromine, or iodine, to an alkene resulted in Markovnikov addition of HX to that alkene. Markovnikov addition refers to the placement of the X group on the more substituted carbon of the alkene. The opposite regiochemistry is observed when radical conditions are used. This is a radical addition of HX to an alkene. And in this case, we saw anti-Markovnikov addition. So the opposite regiochemistry. Because of the presence of peroxides, ROOR, in this reaction, the regiochemistry changes and the mechanism becomes a radical mechanism. Acid catalyzed addition of water resulted in Markovnikov addition, where the OH adds to the more substituted carbon of the alkene, while the H added to the less substituted carbon of the alkene. Oxymercuration, demercuration also does Markovnikov addition, but this one is not susceptible to rearrangement like the others are. So the key difference is that if a substrate were suitable for rearrangement, this reaction would avoid rearrangement, while this one would do rearrangement. We would also see rearrangement in the case of this HX addition. We could also add water in an anti-Markovnikov fashion, and that is through hydroboration oxidation. So in this case, as we see, the OH adds to the less substituted carbon of the alkene, and the H to the more substituted carbon of the alkene. What we also see is syn addition, where the new H and OH are on the same side of the alkene as one another. In the previous examples, we see both syn and anti-addition. We observed addition of H2 to an alkene. We called this hydrogenation. This is a syn addition. So if the stereochemistry were shown, the two new hydrogens will be on the same side as one another. We saw bromination, where two bromine atoms are added to the alkene. In this case, notice that they are added to opposite sides, so this is an anti-addition. If bromine was added in the presence of water, we add one bromine atom and one OH. If instead alcohol were used, we would add an OR. This is called halohydrin formation. And this too, like bromination, does anti-addition. Notice the bromine and the new OH are on opposite sides of one another. And the OH adds to the more substituted carbon of the alkene. We saw three different ways that we could add two hydroxyl groups to the alkene. One was an anti-addition, and in that case, a reagent called peroxy acid was used. So a common one is MCPBA, metachloropurbenzoic acid, or just a peroxyacetic acid is used, followed by acid treatment. The first step of this formed what was called an epoxide. As an example, this epoxide could form, plus it's an enantiomer. That's after step 1. If subsequently treated with acid, the epoxide ring opens to form this dihydroxylated product. If the alkane were just treated with MCPBA, the epoxide would be isolated. It is also possible to add 2 hydroxyl groups syn to one another, either by using an osmium tetroxide reagent followed by NaHSO3 and water, or treatment with potassium permanganate, sodium hydroxide, and cold temperatures. In both cases, syn addition occurs and both enantiomers form. The most unique of all the addition reactions is oxidative cleavage. In this reaction, the carbon-carbon connection is completely severed, not just the pi bond. And at the sites where that carbon-carbon connection is severed, new carbonyls form, or CO double bonds form, to replace the 2 bonds that were broken. This reaction occurs first by treatment with ozone, O3, followed by treatment with DMS, or dimethyl sulfide. We saw very similar types of reactions occurring with alkynes. As a reminder, alkynes are carbon-carbon triple bonds. So like alkenes, alkynes can undergo HX addition. If just one equivalent of HX is added, it is a Markovnikov addition where the X goes on the more substituted carbon of the alkyne and the hydrogen on the less substituted carbon of the alkyne. If 2 equivalents or excess HX is added, now we also see Markovnikov addition, but 2 equivalents are now added and both pi bonds are lost. Both X's end up on the more substituted carbon of the alkyne. Addition of water can occur under acidic conditions like we saw with alkenes. However, a mercury reagent is needed, particularly with terminal alkynes, to help accelerate the reaction. In the case of an alkyne, when water is added, overall an oxygen and 2 hydrogens are added to form what's referred to as an enol. This is a Markovnikov addition, where the OH ends up on the more substituted carbon of the alkyne and the hydrogen on the less substituted carbon of the alkyne. But as a reminder, these enols rapidly tautomerize to the keto form. So the final product upon addition of 1 equivalent of water is this ketone, when conditions are used that result in Markovnikov addition. When hydroboration oxidation occurs, we saw with alkenes that does an anti-Markovnikov addition, and we see the same thing here, that upon formation of the anti-Markovnikov addition enol, where the OH adds to the less substituted carbon and the hydrogen to the more substituted carbon, that enol can rapidly tautomerize under these basic conditions to form the aldehyde functional group, resulting in the addition of overall 1 water molecule. Alkynes, like alkenes, can undergo addition of halogens. If 1 equivalent is added, the alkene remains and 2 halogens have been added. If 2 equivalents are added or excess halogen is present, 4 overall halogen atoms are added. Notice that these added anti to one another, like they did with the alkene addition, or on opposite sides of one another. That stereochemical implication is lost, though, when 2 halogens are added to each carbon. Like alkenes, alkynes can undergo oxidative cleavage, where the carbon triple bond connection is severed completely for the internal carbon of the alkyne 3 bonds are broken, and therefore 3 new bonds to oxygen form, 1 carbonyl and 1 OH. For the terminal end of an alkyne, CO2 is produced. So 4 new bonds between carbon and oxygen form. Importantly, we saw that terminal alkynes can be lengthened to longer carbon chains by using a strong base, such as NaNH2, to pull this proton off, and then a subsequent SN2 reaction can be performed in which this nucleophilic carbon reacts with an alkyl halide to lengthen the carbon chain. So now the terminal alkyne has been made into an internal alkyne, and a longer one at that. We saw that alkynes can undergo hydrogenation or H2 addition either in a syn fashion, where one equivalent of H2 is added using a poisoned catalyst called Lindlar's catalyst, leaving an alkene that is cis. Multiple equivalents of H2 can be added if excess H2 is present, and a catalyst like platinum, palladium, or nickel. Or if sodium and ammonia are used, 2 hydrogens are added, in this case anti to one another, to form the trans alkene. Lastly, we learned that alkynes can be formed by elimination reactions. So if we have a substrate with 2 good leaving groups on it, either on the same carbon or on adjacent carbons, back-to-back elimination reactions can occur, in which a hydrogen is removed with a strong base, pi bond is formed, and the leaving group is lost. And then the second hydrogen is removed, second pi bond is formed, and a second leaving group is lost to form an alkyne. So both of these examples are means of forming alkynes by elimination reactions.